for inviting me, and particularly Damien, who I used to work with in Tyndall in Ireland. And we both have moved on, and I'm now at the University of Nottingham, but in Ningbo, China. So Nottingham has 3 campuses. We have the main campus in China. We have a little satellite campus in the United Kingdom. Oh, sorry. And also a campus in Malaysia. So I've just moved there a couple of years ago, or less than a couple of years ago. I will mention electronics, not so much molecules, but I will mention molecules. And I'll even say something about spin. But really what I'm going to talk about is semi-metals. I'm having no luck today. There's always one, right? Yeah. One talk. Yeah. Yeah, it should be. I'm very sorry, folks. Let's try again. Okay, there we go. That's the famous Trent building at the Nottingham campus, and they have replicas in each campus, so we have a bit of an identity. So anyway, I'm going to talk mainly about electronics. I think everybody in this room knows about this, but I'll go ahead and say it quickly. But I'll be talking about field effect transistors and how you can try to make them in semi-metals. Of course, you know that you have to create a junction. You have to create a PN junction, actually 2 back-to-back PN junctions. And then I have an energy barrier, and I put a gate on top of it, and I have a switch, as long as I can control that barrier height. And essentially, that's what a MOSFET is, metal oxide semiconductor field effect transistor. We're going to try it with a different material, and I'll just talk about that. But before I do, I want to, we did do a lot of molecular electronics while I was in Tyndall, but we also worked with some of the big microelectronics manufacturers. So we had to worry a little bit about what they wanted. So they like ideas that are crazy, but on about the 5 to 10 year time scale. So this is probably more like a 5-year time scale, what I'll talk about. But anyway, the wiring problem was something that was a big problem in the late 1950s. And there was a summer intern at Texas Instruments. I grew up about a mile away from Texas Instruments, where Jack Kilby was given the problem to solve the wiring problem. His solution was the monolithic circuit, that beautiful piece of junk in the middle. And then shortly after that, Fairchild showed that you could make something that looks very much like the modern integrated circuit. What you're seeing are the metal lines that are interconnecting 4 transistors to make a flip-flop. Kilby got the Nobel Prize. Unfortunately, Fairchild died a little bit before it was awarded, so he didn't receive it, but they're both credited with inventing the integrated circuit. Just to make a side comment, we're back at the wiring problem. Because if you look at an integrated circuit today and you do a cross-section, the transistors are the bit down here, the little bit, and most of it's metallization, wires, and it's a mess. So one of the biggest problems in microelectronics today is not what I'm going to talk about, transistors. It's actually, we're back to the wiring problem. All right, so what's happened? There were a couple of transistors in 1960. In 1965, Gordon Moore said, well, look, we're doubling the number of transistors every 2 years or so, so what's going to happen? And if you just think about the problem, this is the example of the chessboard. If you start out with the first square, put a grain of rice on it, double it, next square, double it, double it. So you see you got 1, 2, 4, 8, 16. So what happens by the time you've doubled it 64 times? Well, we've had in the microelectronics industry something like 25 to 30 doublings, maybe more. But if you did it 64 times, you would have, whatever this number is, grains of rice on the final square. So this is what's been driving microelectronics. It's basically complexity. And they've been doing that by making transistors smaller and smaller. And that's basically what most people think is Moore's Law. But actually Moore's Law is also about economics, but we'll save that for another day. So anyway, we have, if we roughly guess, we're probably somewhere like in here in the board. So basically that's how many transistors we have on a typical microelectronic chip. Put it another way, we have roughly, we've exceeded per chip, the number of transistors per chip exceeds the world population, not in people, but in transistors, which is what, about 7 billion, 8 billion, I don't know right now. Or we're soon to have more transistors on a chip than stars in the galaxy, although we don't know exactly how many stars in the galaxy there are. It's actually, you know, they say 100 billion, I forget what it is, a very large number anyway. So anyway, this is this incredible complexity. But as we did that, we did it by making everything smaller and smaller. So if I looked at, say, a silicon nanowire and it was 60 nanometers by 20 nanometers by 20 nanometers, I'd have roughly 1 million atoms. And if I took a reasonable level of doping, I would have about 1,200 dopant atoms in that volume. So that's the number of impurity atoms that I need to make it either p-type or n-type. But as we go smaller and smaller, if I have a nanowire that's 6 nanometers by 2 nanometers by 2 nanometers, and I want to maintain that doping, I have to have precisely 1 dopant atom in the nanowire. That's tough when you're trying to do 100 billion of these things on one chip, right? It's quite a challenge. It's actually, we're not far off that point. In the current technologies, they make something called a FinFET, which is a rectangular piece of silicon, which sticks up like this, and its width is about 8 nanometers. So in your iPhones and all that, you have 100 billion or so, well, probably not 100 billion, but 10 billion nanowire transistors. So it's quite a manufacturing job. But I just don't need to dope, I also need to make junctions. I need to make a P plus and an N plus region to make my transistor. And we like to think of it like this. Here's the P region, here's the N region. But even in conventional electronics, you have to, I don't know if that shows up, but you have a graded junction. But as you go to very, very small scales, you can't even talk about a p-n junction. Because if I try to make something atomically abrupt with a few dopant atoms here, even one dopant atom that diffuses to the other side completely changes the junction characteristics. So if I want to make transistors at 1 or 2 or 3 nanometer length scales, it's going to be very difficult. So a friend of ours, Jean-Pierre, at Tyndall said, well, let's not make junctions. Let's just take a uniform piece of silicon and dope it very heavily and use the gate to turn it off. So essentially, if I don't do anything with the gate, it's just a resistor, you know, a heavily doped piece of silicon, and I pinch it off with the gate. I stop the current flow. And you go, oh, that's brilliant, that's really simple. And he did it, they made them, and they work quite well. They made P and N type transistors, but these were on a few tens of nanometer or less scale. Why didn't they do that in 1960? Why bother with making junctions? And the idea is quite simple. If I have a heavily doped piece of silicon and I try to screen it with I try to gate it, well, if it's metallic, the screening length isn't going to go very far. So it's actually a true nanoscale device because the body of the transistor has to be thin enough that I can gate it. Okay? So it's a cool idea, very simple, and you can see it's easier to manufacture than a PN junction type device. So it got a lot of attention. Jean-Pierre came to myself and some colleagues and said, this is really interesting, how far can we scale it? So we said, okay, we'll put a 1 nanometer device. So the cross-section of the nanowire is 1 nanometer. We put a 3 nanometer gate in it in a simulation, okay? And we put dopant atoms in there, and if you see something like this, that's a good N-type transistor. If you see something like that, it's a good P-type transistor. It seems to work from the physics. However, under the gate, we had 1 dopant atom. If you move that around, the characteristics change substantially. The other thing is, what happens when you make things very small is you get quantum confinement and your band gap grows. So the dopant level, the impurity level, was no longer close to the conduction band, could not thermally ionize. But the dopants were in there at such a concentration that they formed what we call a Mott conduction band. Basically, you basically have a Hubbard model of all the dopant atoms in a line along the wire which become conducting. So even though it looks like a conventional transistor and it looks like it behaves like something macroscopic, one, you can't manufacture it realistically. It'd be very difficult. And two, the physics is completely different than what would you be doing on, say, a micron scale. So, okay, so that's the point there. But, you know, whenever you do a simulation, you always have this fear that somebody's going to go out and actually make it and measure it. And that's what happened a couple of years later. A group in Japan said, well, let's see if we can actually make a junctionless transistor that's 3 nanometers. Now, that's not a nanowire device. So there's a very, if you look into the screen, it's a very wide device. But nonetheless, they have this V-groove gate here. So basically, they make a gate that comes down to a point so that they can make a very short channel in the transistor. This is the channel right there. And it worked. And it actually has good characteristics for turning it on and turning it off, which is a big deal in digital electronics. So that's pretty cool. So we said they couldn't make it, but you can make it. But again, this is one device. You need about, 100 billion or more, reproducibly on a single chip, let alone I don't know how many on a wafer. Okay, so that's the junctionless device. But that's not what I came to tell you about. Okay, so we said, okay, you got rid of junctions. Can we get rid of dopants? That's the idea. We just, okay, it's easier to make transistors without junctions. Would it be easier to make them if we just forgot doping altogether? And you say, Jim, you're crazy. Yes, and I'm very proud of that. But anyway, I hope that I'll convince you that I'm not too crazy. So basically, if you go through the various band structures, a very simple view of the band structures, an insulator or a semiconductor is essentially the same. A semi-metal like graphene has a 0 band gap. A material like bismuth or antimony, we would say, has a negative band gap. Looks like a semiconductor, but the bands overlap. And of course, you have your metal. And I mean, this is known for some time. This is work from Dresselhaus's group at MIT. And what you're seeing here is, as you make the film very thin or the nanowire very small cross-section, the band gap increases very dramatically at small dimensions. So something that was metallic, here or here, becomes a conductor. So this is why the silicon doesn't really look like silicon if you try to make it at a few nanometers. Its properties, its physical properties, aren't that great for electronics. It becomes a wide bandgap semiconductor, and it's hard to dope. So how can we use this? So we can try really hard to manufacture something that's difficult, or we can try a few new ideas. And the idea is very simple. If I take a wide region, so a thick nanowire of a semi-metal, it's metallic. I narrow it in the middle, it's a semiconductor. I let it grow thick again on the other side, it's a metal. So if I have a metal next to a semiconductor and the band alignment's okay, I have a Schottky barrier diode. So instead of making the diodes from PN junctions and impurity profiles, or making a forget the word now. Not the opposite of heterostructure. I have to make 2 different materials butting up to each other. I'm able to make Schottky diodes in principle with a single material, but by simply changing the shape. Now I've taken the problem, which was difficult, and turned it into another difficult problem, which is how do I narrow something like that, at very small, tight geometries. But nonetheless, it's interesting for several reasons. From a simulation point of view, you can show that indeed these sorts of things should work. By simulation, it's standard stuff. It's density functional theory with the non-equilibriums, Green's function, et cetera, et cetera. I think most people here have heard about it. So they're accurate simulations, but they're not by any means foolproof. But they do give you a pretty good indication of what to expect. And what you get is a pretty good behaving device. This is basically when you're trying to turn the device off, how steep that is how good your transistor is, essentially. And this here is, you want good turn-on current. You want to be able to, when the switch is on, you want to be able to do something with it. So we said, okay, let's make one. Let's do it. This is where the story gets a little bit, less exciting. there's a lot of challenges that we ran into. So we work with a group in Jülich, where they do a lot of MBE of bismuth telluride, predominantly for topological insulators. But for their test wafers, they make really high quality bismuth. And they give us these test wafers and we try to process them. Now this is also some of the work from Dresselhaus's group and so forth. But bismuth is kind of an interesting material in its own right. You could even think of it as a 2D material because it forms layers with one atom at the base, puckered to 3 atoms at the top, which are in turn bonding to 3 atoms down. So it's very much like typical 2D material. And it has really, in this 1-1-1 hexagonal direction, it really does look like a layered 2D material with weak interactions. It's really exciting for electronics because it has the highest mobility of any elemental material, by far. It has an extremely high electron mobility, but that's in bulk. So we'd be very curious if we can maintain that advantage of mobility, which gives you high current and high frequency operation, right? The faster the electrons move, the more current I get, and the faster I can switch it. So we thought this was a good choice, and we had some wafers, so let's try to do it. So first thing is, here's an example of one of the layers they're growing that's 5 nanometer, and that one. There is a structural phase transition as you start to grow these, which is giving us some kind of questions we can't answer. But anyway, so basically what happens is we do the measurements, 4-point probe measurements on these thin films, and you see some nice things. This here is the temperature dependence of the resistivity, which shows that it should be a semiconductor. This is also just showing you that bulk bismuth is much more conducting. These are typical metals down here. So it does look like, experimentally, it does look like a semiconductor. Other people have reported similar measurements. So if you make it thin enough, it does look like it becomes semiconducting. But the great news for us is not so much the carrier concentration, but the mobilities. The electron mobilities that we measure are about 3 times higher than silicon at room temperature. And that's large silicon. So when you get down to these very small lengths, you have a lot of different surface scattering. You have all kinds of effects that kill your mobility. So that you can do that in these very thin films, it's a big deal because the industry paid, I don't know, hundreds of millions of dollars just to strain silicon to get incremental changes in the mobility. So to say that, we can improve it by a factor of 3, people start to get excited. Of course, we haven't manufactured anything yet. Okay, so the first thing we tried to do was make a diode. And the idea is relatively simple. You take the thin film, you mask one side of it, and you etch for different times, and you get different thicknesses on the other side. You put some contacts on it, and you measure the current. And if you just etch it for a short time, it just stays resistive. You etch it for a little bit longer, and you look at the temperature dependence, you can see that at low temperatures, you're starting to get an asymmetry. And if you etch it for a very long time, and this is a catch, it's only about 4 nanometers thick now, so we're not really sure what we have at the end. But it does look like it rectifies. It's not a good Schottky diode. Matter of fact, it's quite a bad diode from electronics point of view, which is strange because you would think since you don't have any interface, it's the same material. The bonding isn't interrupted. You would hope that you would have a very, very clean, nice interface. But there might be other reasons for that, which I will suggest in a minute. When am I supposed to finish? Oh, okay, good. All right. So we put a gate on it and said, let's see what kind of transistor we can make. So we had 2 back-to-back diodes. We put a gate on it, put some hafnia down, and put a metal gate down. And all right, big success. It would not gate. You get little wiggles in the current, but actually it just would not gate. We tried different oxides. We tried many, many different things. Usually if you have something like that, you think, oh, my interface is poor. I have a very poor interface. There's charges at the interface. The gate can't get down to control the channel. However, when you start talking to people in the community, you go, well, of course, there's these well-known bismuth surface states, And we said, oh, okay. Yes, we knew there were well-known surface states, but we thought we had passivated. In other words, we thought we had eliminated the surface states. And this is where things get very complicated and quite a little bit challenging for us with bismuth anyway. The first thing is if you form, this is DFT calculations on the structure. This is the 111. This is the normal direction. If you look at Gross direction this way, this is what normally happens. You get these bilayers. But if you put a covalent bond up at the top to try to remove anything happening at the surface, the electronic structure at the surface, you get a reorganization. What happens then is you then get this very weakly bonded structure down here, but the surface states just exist here now. If you try to grow an oxide and you try to simulate that, it looks like the oxide does not bond with the bismuth. It actually seems to form also sort of a layer structure. If you increase the thickness of it, you lose that nice structure that you see there. The red atoms are the oxide. But what happens is you still don't get any real bonding to the bismuth film. So these surface states that you see here, this is the projection from the bulk density. So you know that the yellow, if you can't really see them, but the states down here, they're bulk-derived states. But these states here are 100% associated with the surface. They're there whether you put the oxide on top of them or not. But this is where spin, I said I'd mention spin. They're kind of cool because they arise from spin-orbit coupling. So this band here will have spin up. It's only half occupied. And, well, it's fully occupied, but it's only a spin-up band. And this band down here is spin down. So it's quite interesting effect, but they're very robust. So you'd say, oh, are they topological insulators? People are debating that with bismuth, even in the bulk, but it doesn't matter from our point of view because no matter what you do to them, whether they're topologically protected or not, they're very difficult to get away from or to get rid of. So that kind of has posed us a few challenges. We're looking at different passivation techniques. But we're also beginning to ask ourselves, well, can you use these states in some spintronic applications? And you'd say, well, it's very nice, they're spin polarized, but you have to remember there's time reversal symmetry. So you're looking along one symmetry direction. If you look at along the other symmetry direction in the Brillouin zone, there's the state switch, the spin. And so if you were to try to pass a current through them, you would lose your spin polarization. So there has to be some way to use them, but we haven't really defined it yet. So that was our first attempt. But we don't give up. So anyway, so this is some calculations we did a long time ago and some other people have done. Actually, there's other people who have done this. But it's basically take a silicon nanowire, put hydrogen on it or put a hydroxyl on it or an NH2 or whatever. And what happens is you get the quantum confinement effect, and that's what you're seeing here. These all have band gaps much larger than bulk silicon, but the actual surface chemistry, due to its electronegativity and the large surface to volume ratio, counteracts the quantum confinement effect. So the more electronegative you make your surface passivation in silicon, you can tune that band gap. And I don't know if anybody's actually measured that in detail. I know that people have measured the band gap widening with different terminations, but I don't know if there's ever been a side-by-side comparison on the same system. We were looking at alpha tin because in very thin layers you can stabilize it. It's not stable in the bulk. There's famous historical stories about buttons that once they froze, they became alpha tin and fell off. But anyway, it's very much, anyway, alpha tin has the same structure as silicon. It's a diamond lattice, and it's a semi-metal, zero band gap, but it has somewhat conventional chemistry in the fact that the bonding is very directional. In bismuth, less so, very much more complicated. And what you're looking at here is basically if I put fluorine on the surface and I pull a lot of charge out, that means I have a lot of positive charge stuck in the wire. It looks like a coax cable. And basically, I get this difference in potential. This difference in potential is what's giving me the difference in the band gap. So we said, okay, oh, by the way, oh, I don't actually have it. What you can do then is you can take the quantum confinement effect and make a very thin film, and if you choose your surface termination correctly, you can close the band gap. So I'm back to the situation where by taking a single material, if I can pattern one side with one surface termination and pattern the other side with one surface termination, I have a metal region next to a semiconducting region, and I haven't used any doping. We haven't actually done this experimentally yet, but we have done some calculations. This is basically the region of the thin film, or the nanowire in this case, which the band gap has been closed, so I use one termination here. So you see it's metallic. The local density of states exists everywhere. It's a metal. On the other side, we let the quantum confinement do its stuff. It opens up the band gap, and as you see here, this is very typical of a Schottky junction, metal semiconductor junction. And what you can see here is when I have this is actually hole transport in this case, but when I finally start tunneling from the Fermi level into this valence band here, I get current. You get a very large current peak there. But if I try to go the other way around, I can't get charges through there. These are sort of like what you see sticking out here are evanescent states from the metal surface in the band gap, or forget the other word. Anyway, these are states that are, but they're not enough to actually turn the device on. So you get a nice rectification simply by changing the surface chemistry on a thin film. So again, if I can make a diode, and if I can make two back-to-back diodes, and if I can put a gate on it, I can make a transistor. So this is where we're kind of looking at the moment. Can we actually do this? Would it be easier with this material and using these ideas rather than fighting the bismuth states? We don't know. So it's work in progress. It's sort of molecular, but anyway, so the idea is pretty simple. It's basically by changing the geometry, that was the first approach I told you, you can use the semi-metal-semiconductor transition, or you can change the surface functionalization in something that's already semiconducting to make it metallic. So those are the ideas. So just to summarize what I told you, it's going to be next to impossible at very, very small scales to dope. I think that's pretty much accepted. The conventional doping schemes aren't that just not going to work. The semi-metal, the semiconductor transition, I believe, is very interesting for electronics. I mentioned that we can change things by the surface chemistry, but what we're doing here is we're trying to make conventional transistors by unconventional means. So that's not going to get us very far. It might get us another 10 years or maybe 12 years, but it's not going to solve the problem, because even with these approaches, you're going to run out of atoms. The other thing is the bismuth films. This is a nice, interesting scientific question, because they have the thermal behavior of a metal and a semiconductor. If you want to understand that, it's not that difficult, but what that actually implies when you try to make structures out of them is quite challenging for us to understand. I don't think anybody in the community understands it at the moment. So I'd just like to thank all the people. You've probably seen their names on the paper. I moved to China. They're helping me out now, and a lot of this work was done in Ireland. So thank you, vielen Dank, and Shishe. Is that correct?